All right. Welcome to Algebra 2 remotely online. You'll see me looking because I have people sitting in my room, but you guys are working on your work. All right, so this is Algebra 2. We are on classwork 151. And our objective for today is to look at some rational functions and apply the rules of rational expressions to rational functions. But before we get started with class this morning, I want to really quick go over your homework from the other day. So go ahead and open up your notebook to homework 150, hopefully that you did this weekend. Quick moment to get all that opened up. Number 2 on your homework should have been t times quantity t minus 3, everything divided by 2. Number 4 should have been z times z plus 2 over z minus 2. Number 6, you have r over r plus s. Number 8 is x minus a over x plus a. Number 10, 2t minus 1 over 2t plus 1. Number 12 is negative, so you had to factor the negative out of something. 3 plus 2z over 3z plus 2. And then number 14, we have p plus 5 over p minus 1. Now 16, 18, and 20 were a little bonus in case you did them. 16 should be 1. 18 looks like the numerator is, let's see, only thing you could factor out of the numerator would be an r. The only thing you could factor out of the denominator would be an r. So you have 1 plus r squared over 1 minus r quantity squared. And then 20 is t minus c over t plus c. You didn't have to do them, but if you did them, those are the answers. All right, what I'd like to go over today really quick is to refresh your mind on what a function is. A function is just a little bit more than an equation because what a function is going to turn into is a graph. So a function is true for all points that could potentially make it true. So we looked at functions when we were doing graphing, and the real simple way to think of a function is by using a function machine. You put something in, you do the function to it, and you get something out. So if I put in a 1, I get something happens with the function, and then I get something else out. Remember, a function is only a function if every input has exactly one output. So we saw that when we were doing mapping. Let's bring it back. So I had, say for example, 0, 1, and 2, and then over here I had 3, 4, 5, and 6. Make sense? So I had 0 goes to 3, 1 goes to 4, and 2 goes to 6. Actually, let me move the 5 over here. And 5 goes to 6. We equated this to a vending machine. If you can remember the vending machine example, where I press a button and I get exactly one thing out. I don't press the button for Sprite and hope that I get a Sprite. I press the button for Sprite and a Sprite should come out. I press the button for Coca-Cola and a Coca-Cola should come out. I don't press the button and then maybe I get something, maybe I don't get that thing. So that's the one output for every input. Now, could I have two buttons for sprite? Absolutely. I could have a button that's number 2 and I can get sprite out, and a button at number 5 and I get the same thing out. I can get the same thing out, I just can't put it in and get two different answers out. Hope that makes sense. So in more refreshing of your memory, we have the vertical line test, which when I had my coordinate plane, this marker's running out, and remember I had the vertical line test that said only one vertical line touches, the graph is only touched by one vertical line at a time, which in effect just says each x has exactly one output. So that's our refresher of our function subject matter that we went over a while ago. Now let's see how this applies to rational expressions. And remember, we're going with rational expressions as opposed to irrational expressions. Remember, remember, remember. So let's go ahead and take a look and talk about something that looks like this. We have f of x, remember, which is just function notation, so nothing that you haven't already learned. Alright, and it's going to ask us to state the domain and all the zeros of f. Oh, can't. So this will be A, state the domain, B, the zeros of the function. And remember, that is when the function equals 0. So let's go ahead and think of what is the domain. Well, let's think of our restrictions here. Am I going to have any restrictions? Because when I'm dividing by a number, there's only one number that I cannot divide by, which is, hopefully you're thinking in your head, 0. You cannot divide by 0. So I can put any number in here, and any number squared, is it going to get, and then I add 9 to it, is it going to give me 0? Answer is no. Even if I had -3, -3 squared is -3 times -3, and that would give me 9 plus 9, which will give me 18. So my domain is all real numbers. Okay? We'll worry about the zeros of the function in a second. Let's do another one of those. So the domain is kind of like the restrictions. Let's go ahead and look at, I am on page 228. Let's go ahead and look at the oral exercises. So go ahead and get your book open to that. So I'm looking at the oral exercises 7 through 15. Okay? The directions say, find the domain of each rational function and the zeros of f, if there are any. And this will be easy to talk about the zeros, and then we'll go back to this example. So we have number 7. F of x is equal to x minus 2 over x. What's the only thing x cannot equal? Hopefully you're thinking to yourself, 0. Right. I cannot divide by 0, so my domain for number 7 is all real numbers except 0. So number 7, you would write domain x such that x is all real numbers, that's our symbol for all real numbers, except 0. Does that make sense? So that's our notation for that. Number 8, What's the only thing I can't plug in for x because I will get a 0? And I'm really only looking in the denominator. I don't even have to look in the numerator because I'm most worried about the denominator and what could possibly make a 0 down there. So the only thing I don't want in number 8 for x to equal is 2, because that'll give me a 0. Anything else will give me an integer or a decimal. Number 9, the only thing I don't want x to equal, give me a 0 in the denominator, is 1. Does that make sense? Number 10, the only thing I don't want x to equal is and I'm thinking to myself, what's my restriction? What do I not want, what can I add to 1 and get a 0? Which is negative 1. So negative 1 plus 1 is going to give me a 0. So on number 10, my domain is anything except for 0. The domain, remember, is on the x-axis. Anything I can plug in for x. Number 11, let's think. What my domain, we don't want my domain to be. Looks like it could be anything. Yeah, looks like it could be anything because a negative number squared, number 11, could be all real numbers. Number 12, we don't want our denominator to be 0, so we have 2 minus 2 would give me 0, so our domain is anything except 2. Number 13, we don't want our domain to be 0, so since I have x minus something, I don't want my x to be negative 1, and I don't want my x to be positive 1, because 1 squared is 1, 1 minus 1 is 0, and negative 1 squared is 1, 1 minus 1 is 0. So all real numbers except for negative 1 and 1. Then 14, let's think about what that would be. Should be all real numbers because you're adding 4, and anything squared plus 4 is, even if you have 0 squared, you're still going to have positive. And then number 15, we want, since I'm subtracting 4 in my denominator, I hope that makes sense to you. If not, email me back and I will help you make sense of that. I don't want anything that can equal 4. So 2 squared is 4 and negative 2 squared is 4. So my restrictions are going to be all real numbers except for 2 and negative 2. So that should work there. Go ahead and think about that for a minute. I'm missing you guys thinking of questions that you would ask me in class. Alright, let's go back to the zeros of our function. Actually, what I'm going to do is pause this video because I'm getting to 13 minutes and it's going to take me longer to upload a longer video. So I'm going to pause this and then come right back.